Hey guys, so for your first online lab, we're going to be doing radioactivity. So this is radioactivity. Before we talk too much about radioactivity itself, we have to understand what's called nuclide notation. So we'll say nuclide notation. And basically all you need to understand about this is it's a way of identifying a certain element's isotopes. Because each element has a certain number of isotopes, which just means different numbers of neutrons. So in particular, an example of an element that we're going to be using today is called cesium-137. So the way that we write that is cesium, the elemental symbol, 137 at the top, and then the bottom is 55. So let's talk about what these numbers actually mean. So this bottom number here, this is the number of protons. So this is what determines what this element is. If this number changes, then the element itself changes, right? So this is also known as the atomic number. Okay. So the top number here, this guy, that would be the number of protons plus the number of neutrons, right? And this is also known as the atomic mass. So this number can change because we can change the number of neutrons, which would mean we have a different isotope, but it would not change the element itself. Not necessarily wouldn't change the element itself. So this is really all we need to know about nuclear notation. So we'll use this now, and we'll talk about kind of the different types of decay. So decay happens when a nucleus is at an unfavorable position or an unfavorable energy level, in which case it'll emit or it'll radiate a particle in order to be in a more preferable energy state or a lower energy state, right? So if an atom or if an element is going to be unstable, then it'll decay. And this can happen in one step, it can happen in many steps, it can happen quickly, it can happen slowly, right? It just depends on the type of material we're talking about, and it also depends on the type of decay that we're talking about. So there are many different types of decay, but the ones that we're going to focus on are just three. So we'll talk about these types of decay. Right, and the first one that we'll talk about is called alpha decay, right? And then alpha is whenever we have our parent, what's called the parent particle or the parent nucleus, right? Where again, this is just the parent particle. That's why we have a P. This top number is the atomic mass. The bottom number is the atomic number, right? That's a Z. So this will, under alpha decay into, it'll emit a helium atom, and a helium has a atomic number of 2, and then it also has 2 protons. So it's emitting 4 total particles, or 2 protons and 2 neutrons, right? Which means our parent then is going to be left with 4 less for the atomic mass, and it's going to be left with 2 less for the atomic number. So we write Z minus 2. And then this, what's left over, is called the daughter particle. So we denote it with a D, right? So for alpha, we have our parent in the sample. It emits a helium atom in order to become a more favorable energy level, or to become more stable. And then we're left over with this more stable daughter particle. Okay, so that's alpha. For beta, which is the next one, we have, again, whatever our parent particle is for any given material. And then for beta, it'll actually emit an electron. Okay, and technically one of the protons will turn it into a neutron, okay, which is the same thing as, we can think of it as emitting an electron. Okay, so what we're left over, you can see that this doesn't change the atomic mass, but it does change the atomic number. So what we're left over with here is A is the same, and then our daughter particle will have one higher atomic number. Okay, so this is what we call a transmutation. Okay, alpha is also a transmutation because the atomic number changes, which means the element, the daughter particle, becomes a new element. Okay, the final one that we'll talk about is called gamma. Okay, so we again start with our parent, and then we decay into, and we release a gamma particle. And you can see here that it doesn't change the atomic number and it doesn't change the atomic mass. Okay, so this is just only emitting energy. Okay, there's no actual particle, or the gamma particle being released is just a particle of energy, or a photon, right? So this is going to be plus. Nothing changes for our daughter particle. Okay, well, the total energy would change, but the atomic mass and the atomic number don't change. Okay, so it's just a shifting of the positions of the protons and nucleus, or the protons and neutrons within the nucleus, and that shifting in position releases energy in the form of a gamma particle or a photon. Okay, so these are the three main types of decay that we're going to be talking about. We'll do an example here, and the example that we'll use is going to be cesium. So our example is cesium because that's the element that we're going to be using in the lab. Okay, and cesium is interesting because 5% of the time, and this is specifically cesium-137, we should write that down. So 5% of the time, it just does a beta decay. So we have the 137, we have our 55, which is the atomic number. It will beta decay, which means we are emitting an electron, right? And so then what we're left over with is 137 barium, and then 56 in the denominator. And barium has an atomic number of 56. So we actually transmuted this, right? Because again, beta, you transmute it. You increase the atomic number by 1. So 5% of the time, it does a beta. This is again beta. And it goes directly to barium 137, okay? Now, the other 95% of the time, there's an intermediary step before it goes to barium 137, okay? And this intermediary step is going to be, instead of cesium, it's still going to beta decay, but instead of beta decaying into barium 137, it's going to beta decay into something called barium 137M. Okay, which is just a higher energy barium 137. So this M just denotes that this nucleus of barium 137 is at a higher energy. Okay, and so that should give you kind of a clue as to what the next step in this decay will be before it comes to a stable barium 137. Okay, so the next step then, we take this barium 137M, barium 137M, and this is atomic number 6. We take that, now becomes the parent particle, right? And then this is now going to decay, and it's going to gamma decay, right, into just barium 137. So for this one, there's 2 steps before it finally reaches its final stable state, right? It beta decays. This beta has a less energy than this beta decay that happens 5% of the time. So we have a lower energy beta decay to barium 137M, and then we get rid of that extra energy left over through a gamma decay, and then we're still left over at beta 137. So you can see that we can undergo 2 types of decay for cesium, right? We can either beta, we'll get some beta particles coming out, and we'll also get some gamma particles coming out. An easier way of looking at this, because it can get kind of confusing looking at this, is to draw kind of like they almost look like energy levels, but we call them decay modes. So we'll come back up here and we'll write decay modes. And then this will be for cesium. And so we start at a high energy level, right? Because it's unstable right now. It's at an energy level that it wants to release some energy. And two things can happen, right? We can either go to this intermediary energy level here, and this will be a 0.1520, and these numbers are determined experimentally, beta decay. Or we can do a larger step, right? And this one will actually have a higher energy, obviously, because it's releasing more energy to get to this stable state down here. This would be an energy release of 174. Sorry, this is a 1. These numbers are in your manuals. If you can't read it, it's not a big deal. MeV, and this is beta, right? And this one goes to, right, barium 137M, and then this one decays directly to barium 137. Right. Now this one you can see is still at a higher energy state. This is still not stable, which is why it decays again. Right. And this time it releases whatever this is minus that, which turns out to be 0.6617 MeV. And then this is gamma. Right. So in this branch it goes to barium 137M, and then it releases gamma, and then they end up at the same spot, but this one does it a kind of a roundabout way. But this actually happens 95% of the time, so this one is 95%, and then this happens only 5% for this one over here, right? Okay, so that's kind of all the intro that we need to talk about. So let's talk about what are you going to actually be doing in the lab. And for the first part of the lab, we'll be talking about attenuation. So attenuation. Okay, so what I mean by attenuation really is you can think of this as shielding, right? Shielding. Because different types of radiation are obviously dangerous, right? This is how Marie Curie died, was from studying too many radioactive materials before it was fully understood how dangerous these materials were, and then she got cancer, correct? So we don't want to be harmed by these radioactive materials, so we have to know how can we protect ourselves from them. And we do this by attenuating the outgoing radiation, or shielding ourselves from the outgoing radiation, okay? And different types of decay will attenuate more heavily, or they can be shielded more readily. Right, so let's think of in terms of alpha decay, right? It's releasing a heavy helium nucleus, or a heavy helium particle. In which case, since it's so heavy, it's going to interact very, very strongly with whichever material that we're using for shielding, and so it's not going to attenuate very heavily, right? It'll be stopped pretty soon, right? Because it'll heavily interact because it's a very large particle. So it'll do a lot of damage for sure going through, but it won't. So it's a trade-off. It does more damage, but you can attenuate it more easily. For beta, right, it's like one step down because we're releasing an electron, so it can still do maybe a little bit of damage, right? But the mass of an electron is a lot less than the mass of a helium. An electron is going to interact much less than a helium particle would with whatever given material we're talking about. It'll be scattered less often. So beta will attenuate less heavily than alpha, okay, but it'll do less damage, okay. And then finally we have gamma, which will attenuate very heavily, right? Because these photons, or these outgoing gamma particles, will react very little with the shielding material that we're using. They will scatter not very often. Okay, but they have a lot less mass, which means they'll do a lot less damage, right? So we'll expect in this order, alpha attenuate more, beta attenuate a little bit less, and then gamma will attenuate the least amount. Okay, so if we want to protect ourselves from gamma, we need to use a much thicker shield, or a much thicker material, in order to make sure we get rid of all of the gamma. Okay, whereas if you're using alpha, a very thin shield might suffice. Okay, where you get into troubles with things like neutrons, which are very massive, but also don't interact very heavily, and so those can attenuate. Those are not attenuated very easily, and they also do a lot of damage. But we're not talking about that kind of radiation today. Really, we're focusing of these three on these two because that's what's happening with cesium. So let's draw a picture of what's actually going on here. So we have our shielding material. We'll say this is our shield, and in this case, for this lab, it'll be aluminum. Then we have our sample here, right? It's sitting on some countertop. The shield will have some thickness, we'll call Z. And then the sample will have some number of particles decaying and then shooting out the radiated particles that we'll call C naught, the initial particles coming from the sample. And then on the other side of the shield, we'll have less number of particles because these get scattered or absorbed, or a number of things can happen within the shielding or the attenuating material, but we'll have less particles coming out than we have going in, which is the point of the shield, right? We have a relationship that relates the geometry of the system to these two different counts, and it's called the Beer-Lambert law. And basically what they found is that you can write the change of the number of particles coming out as some constant value, right? So mu is some constant value determined by the material and by the type of radiation. And then we have times the initial number of particles, right? And we have times the thickness Z of our attenuating material, okay? And this constant mu is actually what we're looking for. And this is called the linear, so it's defined as the linear attenuation coefficient, right? All right, now if we want to look at what happens if we take Z to be the limit of infinitesimal, right? We want to know what happens if our shield is very little. We can write this left-hand side as minus mu, right? If our shield is very, very small, or if our shield is very thin, then that means the number of particles C naught is just going to be equal to the number of particles C. So we can write this as C, and this is going to be dZ, right? And then over here we'll have the change in C. Okay, so now that we have this written out, what we want to do now is just take the integral of both sides. So if we do that, where we're integrating the number of counts, the change in the number of counts from our initial to our final number of counts, right? This would be dC over C if we bring the C over, and that's going to be equal to the minus if we're integrating from 0 to Z, Z being the maximum distance, or this total distance, or thickness of our shielding material, and then we're just left with mu dZ. If you do this integral and solve it for C as a function of Z, so C as a function of Z, so the number of counts coming out on this side of the shield after being attenuated is going to be equal to whatever our initial was times e to the minus mu Z. Okay, so you can see that it's a negative exponential, which means as our thickness increases, we get less and less particles coming out on the other side, which makes sense, right? We can actually write this factor mu in a more convenient way, and it's called the mass attenuation coefficient, so mu m, and we can define that as being the linear coefficient over the density of the material that we're using. So this is defined as the mass attenuation coefficient. All right. All right. I think we should be able to see all that, hopefully. Okay, so using this mass attenuation coefficient in this equation that we got here, we can simplify it even further if we take the natural log of both sides, and then instead of mu, we write it in terms of mu m, right? And if we do that, what you're left with up here is the ln of Cz is equal to the negative mu m rho Z. And this is C as a function of Z. Okay, And if we look at this equation, we can write it in terms of, we can linearize it, right? We can write it in terms of a linear equation. So this would be our y here. This rho z would be our x, and then this negative mu m is our m, our slope m, right? So this rho z we define as being the linear mass. So it's just the thickness times the density, and we call that the linear mass. So if we graph this, or if we look at how this graph will look now, on this x-axis, right, we're graphing the linear mass. On the y-axis, we're graphing the natural log of the number of counts as a function of z, or the natural log of c, right? Initially, when we have a very thin, whenever our linear mass is very small, we have a very thin attenuator, beta is going to dominate. We're going to have a lot of beta attenuation, right? Because we have more beta than we do gamma, and beta attenuates more heavily than gamma does. So what we'll see here is initially we'll have something that looks like this, a very steep line. All right, and this is going to correspond to beta, because initially in this region, the beta is going to dominate the gamma, because beta attenuates very heavily. And then at a certain point, whenever our thickness, so if we just did kind of artificially extend this, at some point, right, at some thickness, we will no longer have any beta attenuation. And then what will be left over at that point is just this gamma, right? So whenever this hits zero, whatever is left over, whatever line we have left over is gamma attenuation, because gamma attenuates much less. So even though we still have we're getting thicker and thicker, we're still getting some gamma particles able to come out this other side of the shield. Over here, it doesn't take very much thickness before we're attenuating all of the beta particles that are coming out from here. So at a certain thickness, we'll get rid of beta and we'll only have gamma. Right. So we'll end up having two lines. One that'll correspond to the beta, and then one that'll correspond to the gamma. Right. And so what we want to find from these lines, right, is the attenuation coefficient, or mu m. And we do that again just by taking the slope of each line. So in this case, we would expect mu m for beta to be much greater than mu m for gamma. Okay, and they actually give you a theoretical value for the mu m of gamma. So you'll want to check to make sure that your beta attenuation is much greater than your gamma attenuation. That's one check to make sure that you did this correctly. And then the other check will be to take this number for your mass attenuation coefficient for the gamma line, so for this line here, and compare it to the number that's given to you in your manual. Okay, and that'll be the first part. So we'll be just varying the thickness of this and getting the number of counts at each thickness, and then we'll graph them. We'll graph the natural log of each count at each thickness of aluminum that we'll do, and then we'll get this graph, and then be able to find these attenuation coefficients. What you'll see next is me actually kind of performing a sample run of how we'll get this data, and then you'll find the actual data sheet for this first part of the graph on Canvas. Okay, so I'll post a data sheet on there. It'll probably say like attenuation data, and then you can graph it and be able to determine all of these things that you need to from this data. Okay. Okay, guys, here we are. Ready to do the first part of the lab. And so what you see in front of you here is the Geiger counter is here, and then the Geiger counter tube is here. Okay, and inside of here, we can place our sample of cesium, right? And the cesium will then start will undergo decay, right, as we talked about in the introduction. And then it'll come up, the particles will strike the Geiger counter tube. This is filled with a gas, and it works sort of like a PMT, where you get one electron or one particle coming in and striking one, and then you get this cascading effect, which turns a very small signal into a very large signal that we can then count. Okay, so each one of these counts will correspond to one radioactive event, right, or one decay event. So how this works is, On here, we can select our display so we can determine the amount of time that we want it to count. You can see this indicator here, and if we increase that, this is in seconds. So if we want to take a 3-second count, right, I would turn that up to 3. If it's set to 0, then we're doing a manual count. Okay, the voltage is going to determine the voltage across this Geiger tube, right? So we need a pretty high voltage in order to accelerate the incoming particle, and in order to generate a signal that we can then count. Okay, so I've already determined what this high voltage needs to be, and it's going to be around 900. We need to set this voltage to. If you were to do this in lab, you would have to do varying counts at different times, at varying counts at different voltages. And then what you would see is that a small voltage, we're not going to get any counts, okay? And then as the voltage increases, we'll start to see the number of counts start to increase, and this will just be with this is also with no material inside of here. So we're doing what's called a background count, just getting what is the ambient number of particles striking the Geiger counter from whatever various sources, primarily the sun, right? And so what we have is what you'll have is, as we increase the voltage, we'll get more and more counts, and then the counts will start to plateau, right? And we want to take our operating voltage at the center of that plateau, which for this specific Geiger counter tube and counter combination ends up being around 900 volts. Now, if we want to start our count now, so we have it set to a manual count, let's go ahead and increase that, because we want to count for about 10 minutes. We're going to do a 10-minute background count. So that means we need about 600 seconds, right? And so if we keep coming here and go to count, if I hit count, it's going to begin the count, and then our timer is going to start counting down, and we'll be able to get a background count. And this is the background that we'll use for the entire experiment. Okay, so we'll be able to determine what is the background that we need to subtract from our counts by doing this. So we'll go ahead and start our count. We'll see that we're starting to get some counts there from the background, obviously. And if we look at our time, you can see that the time is counting up, and it'll automatically stop once it hits 6 minutes. So we will come back. We will come back in 10 minutes and see what our background is. Okay, so the background count is now done. We can see our number of counts here. If we look at the amount of time that it took to do that background, is written right there, right? So 10 minutes, our background was 567. Okay, so if we're doing a 5-minute count in the future, which is what I think we'll be doing, you'll have to take half of this and subtract that from the count that we get for that particular thickness of aluminum. Okay, so this is an important number. This will be included on your data sheet for the attenuation data, but it'll also be it'll be the same number no matter which part of the lab that we're doing. This will be the same background for all 3 parts. Now, if we look here, this is our cesium source. If we open this up, it's encased in amber. Okay, so there's some cesium in there. It's encased in amber. If we put this now into our Geiger counter, and let's just see what happens. If we hit count, right, we can see immediately that the counts are starting to go up much quicker. Right, and that makes sense, because before we were just taking a background. Now we actually have an active radioactive sample in there, which is emitting particles. So of course we're going to get a much larger number of counts. Let's go ahead and stop that, and then we'll reset it. And so what we want to do, right, is we're going to take varying thicknesses of aluminum sheets. So I have a little holder over here, if you want to see it, and there are varying thicknesses of aluminum sheets in here. The first one, marked A, right? This one has a linear coefficient or a linear mass of 4.5 milligrams per centimeter squared. All of these linear masses will be, again, included in your data sheet, so it's not too important what the linear mass is. This is the thinnest one. Okay, so what we'll do is we'll take this and we'll place it above our sample, like so. And that is now going to be blocking or attenuating or shielding the number of particles coming from the cesium. Okay, so if we take another count, right, it might be hard to notice, but it's going up a bit slower, right? Because some of those particles are being attenuated. Now, of course, this is a very thin piece of aluminum, so it's going to be hard to see initially that it is going up slower. Let's go ahead and stop that and reset it because we want to take a count, but we only want to do it for 5 minutes in this case. So we'll actually change our time to 300 seconds, right, which is 5 minutes, and then we'll do that count, and then it'll start counting up, right? So if we come over and we see our counts, you can see that's going. So what we'll do, or what you would have done in this lab, is to do a count, a 5-minute count, wait 5 minutes, record the number, and then take this. Let's just imagine that we've run this for 5 minutes, right? It would have stopped. We would take this out, record our number of counts, and get out the next aluminum sheet, right? So this is B. It has a different thickness, which means it has a different linear mass, right? And we would just insert it in that same slot above, and then do another 5-minute count, right? And so for each of these different linear masses, you'll get a different count. The corrected counts, you'll need to take whatever this count number is and then subtract our background, right? And then you'll be able to do all of the analysis that we talked about in the introduction to attenuation. Okay, so that's pretty much it for this part of the lab. So what we'll do now is I'll go ahead and introduce the next portion, and then we'll come back and I'll show you how to do that in lab. Okay, guys, so for this second part of the lab, what we're going to talk about is the flux of a particular sample, of a radioactive sample, and how that flux changes with distance. Okay, what I mean by flux is really just the number of particles like passing a given area, right, or passing through a given surface area. And how does that change whenever the distance away from the detector changes? Okay, so let's give like one really simple example, and that's if we have the sun, right? And we have the Earth way out here, right? Some distance away, some distance, we'll say 1 AU away, because I don't know what the distance in meters is. But what's important here is that, right, this distance will in some way attenuate. It's not really attenuation, right? But this distance will decrease the number of particles that is going to strike the Earth, which is a good thing, right? Because if it wasn't, Earth would be more like Mercury with no atmosphere. The atmosphere would be completely stripped by the number of particles and the amount of radiation coming from the sun. So what we want to show is that this relationship from the amount of flux coming, in this case from the sun or some sample to a detector, right, is proportional. So the number of counts, right, is proportional to 1 over the distance squared, the distance away from that material squared. Yeah, so this is obviously a good thing, because this is when we talk about a planet being the Goldilocks zone, when we're looking for habitable planets, right? We need to take this into consideration, right? So we want to make sure that the amount of radiation striking the planet is not such that it's completely stripping the atmosphere. Okay, there are other things on Earth like the magnetic field, which protect us from some particles as well, right? But this is really the main contributing factor, is just the distance away from the sun, right? Our magnetic field wouldn't do anything if we were the same distance away as, say, Mercury, right? All right, so what we're going to do here is we want to really show that this has this 1 over r squared relationship. So we'll just take different number of counts at different distances, all right? And so we'll have a graph, right? And what we'll actually do is we'll take the log base 10 of each side. So we'll take the log base 10 of C. And if we also graph the log of r on the x, right? So if we take on this we have on our y the log of C, and then on the x we have the log of r, the distance. It turns out that the slope of this line that we'll get, right, will be equal to whatever the exponent for r is. All right, so in this case, our exponent, right, this is the same thing as r to the minus 2. Okay, so if we take a log graph of C and R, right, the slope of this line in an ideal case would be equal to minus 2, which means we have a 1 over r squared relationship between C and R. Okay, so this is what you'll be doing, right? We'll take C, the counts at differing distances. You'll take the log of both of those values. You'll find the slope and make sure that this is close to 2. Okay, so this part I think is fairly straightforward. So what you'll see me doing next, right, is actually going through this process and showing you how you would have gotten the data. And similar to the attenuation data, this will be labeled as like flux data and on Canvas, and you can use that data to then determine what the slope is and then make your conclusions from there. All right. All right, here we are back in lab. So this will be for the second part of the lab, right? So we're doing the how does flux change with distance. So what we first need to do is take out this Geiger counter tube from this apparatus right here, and we're going to set it inside of these two prongs on this meter stick, right? Okay, so now that we have that set up, we can take, there's another holder down here. Okay, so another one of these holders that we can use. We want to place this about 20 centimeters away from this one. So this one is marked at 30, so we'll place this one at 50. So that distance between the two is 20 centimeters. All right, and then we'll take out, so we can put this piece of aluminum back in here. And we'll take out our cesium source now and place it into this second prong. Okay, there we go. All right, so we can see that the particles will be coming from here and they'll be shooting towards this detector. And we can vary this distance just by moving our cesium here, right, further back. Okay, and we'll do that at varying distances. So we would just take the count as normal, right? We would select our time to be 5 minutes. Our high voltage is never going to change. That's 900 volts still. And then we'll come back to our counts, and then we would hit count. Okay, and then let's just flash forward. Imagine that we had just completed a 5-minute count, so we'll go ahead and stop this, right? And so that we would record whatever our count was right here, okay? And then we would come over and then move this out to the next distance, the next corresponding distance. So 10 more centimeters away. So this would be 30 centimeters apart. And then you would just repeat the process, right? So we would reset our Geiger counter, and then we would just take a separate count at this distance. All right. So this one would have been pretty straightforward, right? Just taking different counts at different distances. So at each distance, you'll record the natural log of the recorded counts, or we'll record the log of the corrected counts, which is just whatever we get here, again, minus the background. And then you'll plot that log graph and be able to determine what is the dependence of the amount of the signal to this distance. Okay? All right, so I think that about covers it for the second part. There is only one more part after this, so we'll go ahead and jump to the introduction for that third and final part, and then we'll come back here one last time to show you how you would have done that in lab. Okay, guys, so this is going to be the final part of the lab. This also should be the quickest part if you were to actually have done it. And what we're going to be talking about is called the half-life. And specifically, we're finding the half-life of barium 137M. Okay, and we'll talk more about what this means in a second. Okay, but before we talk about what half-life is, we first need to talk about why is it necessary to talk about in terms of things in terms of half-life. And it turns out that radioactive decay is not a constant process, right? It actually follows an exponential process, so we can't think of it in terms of like a constant value. So it doesn't decay by the same amount every second or so. So in order to determine, in order to kind of be able to quantify the decay of a particular material, we talk about its half-life. Okay, and how this is sort of derived is we have the rate of change, we'll just call it R, of the number of parent particles within the sample, and this is obviously going to decrease as it begins to decay, as the parent particles begin to decay into the daughter particles. So we can write this rate of decay of the parent particles as the negative because it's decreasing, change in N over the change in T, change in the number of parent particles over the change in time. And we can also write this in terms of a decay constant, lambda, times the number of parent particles, or the number of particles that we're getting. And so this lambda is defined as what we call the decay constant. And as I just said, right, this isn't determined. It's not like constant every second, right? And we'll see what precisely this means in a second. If we write this, just this part, in terms of an infinitesimally small time, delta t. So we have, instead of delta n, delta t, we have dn over dt. So an infinitesimally small change in time. This right-hand side will stay the same. Right, and what we can do is now rearrange this equation and then take the integral of both sides. So what we'll rearrange it like is the integral of dn over n is going to be equal to the integral of negative lambda times dt. And if you actually perform this integral, what you'll see is that we'll get n as a function of t, and it's going to be equal to, as we talked about just a second ago, a negative exponential, right? Where n naught is the initial number of parent particles, and nt is the new number of parent particles at any given time. So if we graph this equation, where on y we have n, and then on x we have t, it's just going to be a negative exponential. So at time equals 0, we'll have n naught particles, and then it'll decrease from there. So at this point where we have time equals 0, that's equal to n naught. Okay, so it turns out that for any exponential, right, we can talk of it in terms of the half-life, and this is convenient because the half-life is the same no matter what our initial setting is. So the time that it takes to increase whatever my initial count is by half is the same no matter where I start. So for instance, if I'm going from n naught to n naught over 2, right, this distance here is the same as if I'm going from n naught over 2 to n naught over 4. So this is not a very well drawn exponential, but you can get what I mean, that if I take this point down and I take this point down, right, the distance from n naught to n naught over 2 and the distance from n naught over 2 to n naught over 4, those distances are the same, or those times are the same, and we call those the half-life. Okay, so for materials that have a very large half-life, it means it takes a very long time for it to decay. If it has a very short half-life, obviously it means it takes a very short amount of time for it to decay into its stable form. So we want to come up with an expression for what this half-life is. And to do that, we just have to realize that at the half-life, at t 1/2, that means that in t or the number of particles evaluated at the half-life, or at t is 1/2, would be equal to half of whatever the initial number was, right? So at this time, this number becomes half of this initial value at the half-life, because that's how it's defined. So if we take this information and plug it back into our equation for the decay of the parent particles, what we'll get is n naught over 2, right, instead of nt, and that's equal to n naught e to the minus lambda t, or the half-life, minus lambda half-life times the half-life. And now these n naughts can cancel out, so we'll have 1/2 is equal to e to the minus t 1/2. And if we take the natural log of both sides and do a little bit of algebra, what you'll end up with is that the half-life is going to be equal to the natural log of 2 over lambda, okay? So all we need to do in order to determine the half-life is to determine what lambda is. And in order to determine what lambda is, we need to put this equation into a linear form so that we can then graph it, and then from that graph determine what the decay constant lambda is. So to make it linear, basically we just take the natural log of both sides. And if we do that, what you'll end up with is the natural log of n. Again, this is just taking the natural log of both sides, is going to be equal to the natural log of n naught minus lambda t. Okay, and you can see that this is now a linear equation. It's linear in the fact that this is our y term, right? This is our b, so our y-intercept. This lambda would be our slope, and the time t is our x. Okay, so if we graph this equation here, we have t on the x, and we have the natural log of n on the y. Instead of getting an exponential, a negative exponential, we'll get just a negative linear line. And then from this equation, you can see that the slope of this line will be equal to the negative of the decay constant, lambda. Okay, so for this next and final part of the lab, we'll just set a timer, and then every 30 seconds we'll record the counts. And then because barium-137M has such a short half-life, we'll actually be able to determine what this half-life is. Okay, if our half-life was much larger, it would be harder to do this sort of experiment because we would have to wait much longer time to be able to notice any noticeable dip in this curve. Okay, so yeah, that's what you'll see next is me kind of going through this final part of the lab and explaining to you the procedure. And then just like the other parts, this final data set of the number of counts versus the amount of time will be on Canvas, and it'll be the half-life .dat. It would be our half-life data set. Okay, so let's go ahead and do this final part of the lab, show you this final part of the lab, and then you'll be ready to do some analysis. Okay, guys, here we are back in lab for the third and final time for this particular lab. So you can see that I've got the Geiger tube back in this apparatus here, so we'll be using this detector setup again. We're done with our meter stick, so that'll just stay back there out of the way. You can see that I've taken the cesium source out and put it back into its case. So we're no longer using the cesium because what we want to actually find is the half-life of the barium-137M, right, which is that higher energy barium. So what I have instead, and why I'm wearing gloves, is this source here. And what happens is you'll push a liquid through the top canister, or the top here. It'll capture the barium-137M that's located inside of this cylinder, and it'll come out the bottom. All right, and if we deposit that onto this tray here, we can then put that tray into our detector and then begin our count and be able to determine from those counts at different time intervals what the half-life is. So the reason I have the gloves on, right, is this is going to be a liquid source. It's not encased in amber and plastic like our cesium source was. And so it's very easy to get some of this on your hands and then forget about it and then later on eat and then have a bad time. All right, so we'll be as safe as possible and wear our gloves. So how this would have worked, specifically if you had been in lab, like after I deposit the barium-137M into this tray, I would put it in, and immediately you would begin to start a manual or a separate timer on your phone for 14 minutes. Okay, and then at every 30 seconds, so at 30-second intervals, you would then record the counts that is being recorded on your counter. Okay, now these counts are going to be going up so quickly that you're not actually going to be able to determine what the exact count number is. So what you would have to do is every 30 seconds, you have to take a picture of this number and then later on go back through your pictures and record what that number is. Good news for you is that you're not going to have to do that. I will have to do that, and then I will record the sample data into the corresponding half-life data sheet on Canvas. So that'll be already recorded for you. So you'll just see 30-second intervals and then counts at each of those 30-second intervals. So let's go ahead and get this started. So we need to set our time. So we'll display. And we want our time to be set to 0 because that sets it to manual, which means it's just going to run continuously until we manually tell it to stop, until we hit the stop button. Okay, so that's set. We set the voltage to 900 as normal. That doesn't change. And then we want to set it so that we're now viewing our counts. Then we're going to go ahead and get this sample ready. So we take the top off, take the bottom off, go ahead and place it in there so we don't accidentally get some radioactive juice flowing on the table. We'll take this is just a bottle of just a eluting solution, so it's just salt and water, so it's a saline solution. We'll take some of that out of here. And then go ahead and insert that into the top of our source there. All right. Now we're going to push the top here, and that's going to push the liquid through here, and then it's going to come out the bottom and into our tray. And we have to be kind of quick about this, so as soon as I push this through. Again, we'll put it back over here. We can see that there's now liquid there. We'll put it into our counter, our Geiger counter tube. And then we'll go ahead and start our counts. Okay, so we're going good. Like I was saying, I'm going to do this part for you. So every 30 seconds, I'm going to go ahead and take a picture of this time here. And then I'll do that for every 30 seconds for 14 minutes, and then get a data sheet that you can then use to do your analysis. All right, so that's going to be it for this first lab. Hopefully this works out okay. If you have any questions, as always, just email me, and we can get any questions answered. But I think this should be a good way of proceeding going forward. So if you have any comments or concerns, just let me know. But yeah, that's where we'll end it for today.